Good morning. Uh, Today we'll discuss about obtaining an expression, obtaining an expression for the leakage reactance, for the leakage reactance of transformer with with primary and secondary coils of equal length. Before going for the further explanation, we need to clarify certain points for the reactance calculation. What are the prerequisites? What are the things? As we have already known from our previous classes regarding the transformer is a constant flux machine. So there is a certain part of the flux which is the useful flux, and certain portion of the flux that leaks in between the LV and HV winding of the transformer, that is called as the leakage flux. So we will revise a bit. Useful flux is that part of the flux which establishes the magnetizing current, and this is responsible for transferring the energy electromagnetically from primary to secondary side, and this is the flux responsible for transferring the energy from primary to secondary side with the principle of mutual induction. And I can define it also. The path of the useful flux is in the magnetic core. So the path of the useful flux is in the magnetic core, and this useful flux is what it is basically responsible for transferring of energy electromagnetically from primary to secondary side. So it is responsible for transferring energy from primary to secondary side with the principle of mutual induction. Now the second term comes as the leakage flux. So leakage flux, we know this is that part of the flux which either links with the primary side or with the secondary side, and is responsible for imparting inductance to the windings. The path of the leakage flux depends on the geometrical configuration of the coils and the neighboring iron masses. So leakage flux is responsible individually associated with the primary or secondary side. Now the important part which we are interested is to calculate the reactance. Now reactance, if we go to our basics also, reactance is what? Reactance is given by XL, and it is nothing but as 2 pi FL, or we can write it as omega L, wherein your omega is equal to 2 pi F. So this is an angular version of the inductance. So here we can see this is omega into inductance. So inductance, how can you define inductance? Inductance is primarily given as the flux linkages flux linkage, how much flux is linked, and this depends upon the number of turns of the coil or the winding divided by the amount of current, so inductance is defined like this: flux linkage divided by the amount of current. So how this is about inductance. Now what about the flux linkage? How do you establish this flux linkage? Flux linkage is the amount of flux associated with the number of turns. So it is given by flux into number of turns, flux linkage. And your flux in itself, earlier also in the previous classes also we have seen your flux is what, in terms of mmf. If you write mmf is what, flux into mmf is an equivalent of voltage, and mmf is an equivalent of voltage, and this is voltage is equal to current into resistance. Similarly, mmf is equal to current's equivalent is flux and resistance equivalent is reactance. So you can write mmf is equal to flux into your reactance. You can write mmf is equal to flux into your reluctance. Reluctance is magnetic equivalent of resistance. In see, again I will write your voltage, your current, your resistance. This is your electrical terminology, electrical symbols, electrical. Similar to this in magnetic, what you will write? Magnetic, it would be your mmf, here it would be your flux, and here it would be your reluctance. This is called reluctance. Here I'll write flux. So again we can write over here your I'll be turning to the next page. So again we can write over here your reluctance, your flux is nothing but your mmf or ampere per turn divided by reluctance. See, your flux is mmf divided by reluctance. In the previous equation, if you go back to the previous equation, to the previous page, here if you can see, mmf is flux into reluctance. So you can write your flux is equal to mmf by reluctance. So it can also be written as mmf into 1 by reluctance. So your 1 by reluctance, this particular term over here is nothing but 1 by reluctance is also known as permeance. This term is also called as permeance. So here you can write this mmf, ampere turns flux, is mmf or ampere turns per reluctance, or you can straight away write this is equal to ampere turns into permeance, and similarly your permeance can be written as 1 by reluctance. Now your resistance was rho L by A. So 1 by R would be A rho by L. So here this term is given as rho, resistivity. This can be written as mu naught by mu R. This is flux, this is the permeability of the air and permeance of the material. So this we will be writing in terms here. So your A comes on top, so this is A, and here you have mu naught mu r by L. So this is your A, and instead of 1 by rho we are writing mu naught mu r, and here you are writing L. So this L is in the denominator because of this. So this is the formula for your permeance. A is equal to mu naught mu r by L. Now these were the elementaries we have to obtain in this particular problem. We have to obtain an expression for leakage reactance of transformer with primary and secondary coils of equal length. So what we'll do is, first we'll take, this is the transformer primary section and this is the transformer secondary section. So this is my transformer primary section and transformer secondary section. So in the primary section I have some flux linkage. I'll be drawing this is my flux linkage and the direction of the flux. Similarly, in my secondary section I'll be drawing my flux linkage and the direction of the flux. So these are my flux linkage and direction of the flux. So there is some length associated here. This is called as LC, this length, and there is some distance of the primary. I can say it as BP, and let this be secondary side, let this be BS, and I have flux linking with this side, let this be phi P, and flux linking on the secondary side, let this be phi S, and there is one more flux that is linking in the duct, or we can say it as a leakage flux. So if this is the direction of the flux from here, you can see this is the direction here, and here we have another direction. Similarly here we have like this. We have another direction of the flux, and it's going like this on top. It's coming like this. See, the direction is coming and remaining. Similarly here, as far as this is concerned, same thing here also. You can see this is the direction of the flux, this is the direction of the flux. So there are some important terms. Now phi P, we can call it as psi P is leakage flux in primary. Similarly, psi S is leakage flux in secondary, leakage flux in secondary. Now we have our psi naught. This is your flux through the duct, Now L naught is your mean circumference of the duct, L naught is the mean circumference of the duct, and you have LC, which I have drawn here. You can see it's the axial length. LC is the axial height of the windings, whereas BP and BS are radial width of primary and secondary windings. BP and BS are radial width of primary and secondary windings respectively. So here, before we go into the calculations and the understanding part, so we have to understand the essential and the important features of the calculation, how we are going to go about it, and how we are going to calculate it. So we have to be very clear with our concepts, and we should not get confused with different type of notations or different books. I've used a particular type of notation, and you can stick with this. A is the width of the radial duct, and this width you can get from, see, there is some distance between here and here, so you can get this width because there is a duct. So here, and keep here, similarly here. So this is A, and this is the width of the radial duct, and radial duct. So here you can see these are the ampere turns of the secondary IS and TS. This is equal to, because we will approximate, this is equal to IP and TP. Now we have to go about our flux calculations. Prior to going to the flux calculations, there are some assumptions which we have made. The assumptions will be set in the following section. A is the width of the radial duct A is the width of the radial duct. A is the width of the radial duct. So there are some assumptions, and this is the calculations which we have seen. So we'll be moving on to the next section, and we'll go for some assumptions prior to obtaining the expression for the leakage reactance of transformer with primary and secondary coils of equal lengths. So the assumptions which are very important in obtaining the expression, the number one assumption which we have made is the following assumptions are considered. The following assumptions are considered. Number one assumption is effect of magnetizing current on reluctance and effect of saturation of iron is neglected. Effect of magnetizing current on reluctance and effect of saturation is neglected. Second is the flux paths are parallel to the windings. The flux paths are parallel to the windings along the axial height. See, this axial height, if you can see from this is the flux paths are parallel along the axial height, and the axial height would remain same. Equal axial lengths for both primary and secondary winding we are considering. So we'll write down equal axial length for both primary and secondary windings is considered. So this is one point. Another is length of mean turn of both the windings is equal. That means TP and TS. LMTP. Length, that is the length of mean turn, also called as LMTP, length of mean turn of both the windings is equal. Another assumption is the primary winding MMF is equal to the secondary winding MMF. The primary winding MMF is equal to the secondary winding MMF. The primary winding MMF is equal to the secondary. Half of the leakage flux in the duct links with the each winding. So you see, this portion is your half this psi naught is your half of the leakage flux, and this is flowing in the duct. So this half links here and this other half links here. So this half of the leakage flux in the duct links with each winding. So you can write down half of the leakage flux in the duct links with each winding. The reluctance of the flux path through the yoke is negligible. Therefore, the reluctance of yoke does not affect the flux distribution. So we are not considering the reluctance of the yoke. So the reluctance of the flux path through the yoke is negligible. Therefore the reluctance of yoke does not affect the flux distribution. And the last point is that the windings are uniformly distributed, and therefore the winding MMF varies linearly from one end to ampere turns at the other end. So the last point is the windings are uniformly distributed, and therefore the winding MMF varies linearly from 0 to ampere turns from one end to other end. Here up I want to wind up my class, and in the next session I'll be deriving the equation, and we will also solve some problems based upon the reluctance calculations. These were some prerequisites required for reluctance calculations, and in the next class we will go for the derivation part of it, and we'll solve some problems based on reluctance calculation. Then we have left with cooling of transformer and the calculation part of that, and voltage regulation. So herein we will be solving some more problems, and with 4-5 more lectures we'll be done with module 3, and then we'll move on to the module 2, that is your DC machines. Hope you enjoyed the class. Thank you very much.